Okay, today we will talk about the introduction to machine learning. We are going to look into other stuff that we need to know before starting learning TinyML, especially the topics in the next sessions. So this is the layout for today's talk. So first, we quickly recap the materials that we have covered yesterday. Then we will talk about it shortly and quickly on neural network. The purpose of this topic is to give you some essential terminologies that you know, the essential terminologies that you need to know later in the next topics. So maybe some of you are familiar, but if to those that are not familiar, I think this short introduction will be helpful. And last, we will talk about some of the tools, libraries that we need to know or use during our TinyML projects or ML projects that we can successfully accomplish our projects. So let's begin start. So to quickly recap the materials that we have covered yesterday, we talked about artificial intelligence, machine learning, and deep learning. And also we have a quick look into different category of machine learning, from reinforcement learning to supervised learning, like regression and classification, and also supervised learning. We gave an example about the clustering. Then we talked about a bit about machine learning and the difference between machine learning and tiny machine learning. And we consider some of the main enablers and limitations in machine learning. Then we consider together the different steps of machine learning process, which first we talk about the importance of data and how we can collect the data, and we need to take into account that finally we need this data for training set, validation set, and test set. So we talk about each of these terminologies in more detail. So and then we discuss about some of the main issues that arise during the data collection steps, such as bias, unbalance, and small data set size. And we talk about some of the straightforward solutions that to mitigate these issues. Then we talk about the data cleaning and data preparation. So we talk about the how to treat with unwanted data, and also with outliers, and how to handle missing data, and how we can extract features and select features that are more important in our problem. And then we consider that how we can split our data set into train, test, and validation, as well as some of the widely known or well-known models for regression, classification, and clustering. Then we talk about the importance of choosing right evaluation metrics. We talk about confusion metrics, and two of the most common issues in the training stage, which is overfitting and underfitting, and we talk about some of the solutions that we can omit prevent these issues. And by the last of the session, we quickly use Python and Jupyter Notebook to run simple machine learning, to see how simple machine learning can be coded in Python. So let's start the topic of today. The first topic is on neural networks. So the first question is, what's artificial neuron? Or so in this case, we need to define that the artificial neuron is inspired, actually was inspired by from the biological neuron. So that we try our best to mimic the operation of a biological neuron as to the best of our knowledge from its actual performance and how does it work in our brain. So as you can see in the left side of the figure, this is a biological neuron. So there are some inputs into the neuron. This neuron actually do some operation on the received signal and then pass it to the neurons in the next to this neuron. So in artificial neuron, we actually have something similar, that we have inputs that go into another neuron, that in this neuron we do some simple operation such as multiplication and summation, and we have output. So this is actually what we are doing here is a mimic of the biological neuron. So what is actually a neural network? When we are talking about neural network, it's a network of neurons. So for example, we are saying that we have a neuron here. If we network these neurons together, is a neural network. And if we densely connect these neurons together by adding more hidden layers and also increase the number of the neurons in each layer, we are making a dense network layer, which the neurons densely connected to each other. So in a neural network, we actually have input layer, we have one output layer, and the other layers that are between the input and output layers, we call it a hidden layer. So intuitively, we can say by increasing the number of the layers, hidden layers, we can solve more complex problems generally. So let's, out there actually, there are plenty of advanced algorithms like CNN or convolutional neural network or for the purpose of image recognition. But for this introduction, let's start with a simple example or application of neural network, which is actually the hello world example of neural networks. As soon as we collected a data set of handwritten digits from different people, which is maybe something similar to this one, and we want to feed our neural network to do a classification and can recognize that number later on seeing input, which is, for example, an image of a number. So let's start to see how a neural network can do this job for us. And during this procedure, we start to learn the essential terminologies of neural network. So we assume that, for example, we want to work in one of these pictures, for example, this 8 that is here. So this picture may be in size of 28 by 28 pixels. So let me take my pen. For example, it's in the size of 28 by 28 pixels. So we convert it to a matrix, which element of each matrix corresponds to the value of that particular pixel. For example, if this is our first pixel, so its corresponding value is a 0, which is, we assume that this image is black and white, which 0 is for the black, and for example, 255 for the white color. So in this case, you can see that those pixels that are white or gray, you can see some number here. At this stage, what we need to do, we need to normalize these numbers. So we can do the normalization by dividing each of these numbers by, for example, 255. And then we convert this matrix into a vector. So if our matrix is in a size of 28 by 28, we want to convert it to a vector of size of which is 28 by 28 is equivalent to 784 by 1 vector. So we use this one as our input layer. So which means this is our first neuron, which this neuron is actually a number between 0 and 1, because we already normalized these numbers. So we use this one as the input of our neural network. And in each neuron connected to all neurons in the next layer. So in this example, you can see that all 784 neurons fully connected to the neurons in the next layer. So here, for the sake of simplicity, I just consider one hidden layer in size of 15. So the neurons from the input are connected to the first hidden layer, and these neurons are connected to the output layer. Our output is in a size of 10, which we have 10 digits, and what we ask our machine is to predict that later can predict the digit based on its input data. So since this is a dense network, let's just focus in one of the neurons to see how does it perform and what actually it does. So you assume that this is one of our neurons in the hidden layer, that all neurons from the input layers are connected to this neuron. So we call, as I told you, in each neuron there is a number, which that number is a range of 0 to 1. So we call this one as activation. Activation is simply 1, is a value between 0 and 1. So each neuron from previous layer that connected to the next layer, there is a weight that this weight show the strength of this connection. If, for example, the activation of previous neuron is important to us, we assign the W in a large number. If that's not important, we reduce the weight here to reduce the impact of previous layer in this specific or particular neuron. So as a first step, a neuron just simply start to do some simple multiplications. For example, as you can see here, it's just multiply the x1 into the W1, and for the second one, and up to the last one. So as you can see, the output of this operation is a number. So this number might be less than 0 or more than 1. While we are interested for numbers between 0 and 1. For this case, we are using a function in each neuron that we call it as activation function. So the job of this activation function is, for example, convert our calculated value from this operation to a number between 0 and 1. So for this purpose, there are plenty of the activation function. Two of the most well-known function are sigmoid and ReLU. Sigmoid is a conventional one. ReLU is the most popular one, and also widely used in deep neural network. So how does it work? If our calculated value is very positive, it's somewhere close to 1. If that is very negative, it's close to 0. And if it's somewhere between here, it can be calculated from this equation. And for the ReLU, is a simple function that just picks the maximum value between 0 and the input value. If the input value is negative, so the output is 0. If the output is positive, that positive number is the output. ReLU is too popular because of its simplicity and is widely used in deep neural network because of this. We are talking about a dense neural network. So when there are a massive number of neurons, for computer, there is a difference to use this function or this function. Maybe in the first impression, we say that both of them are simple, but actually when we are talking about a dense neural network, this makes a difference for computation, required computational power. So that's the function of the activation function. But here we have another parameter, which is a bias. So why we use bias? Actually, the purpose that we are using bias is based on this activation. Actually, the trigger is 0. For example, this trigger can be considered as a reference. If our calculated value here is more than 0, is, for example, perform like this or this. If that is less than 0, it perform like this or like this. So we don't, for some cases, we maybe are interested to change our trigger or the reference. So for example, here, we assume that instead of triggering, I mean by triggering is to activate or inactivate the neuron that we are talking about. It's not a binary like on and off. It's actually a value between 0 and 1. So in this case, if we want to change that reference number, we can change the bias here. For example, if we want to change it instead of 0, we want to trigger on 10, we can assign -10 to the bias, and then we add that bias number here and trigger our neuron based on this bias. So another terminology that we need to know is feed forward. So when we're talking about feed forward, is moving from the input layer to the last layer. So the operation that we discussed in the previous slide was only for one single neuron. We need to repeat this operation in all neurons and also output neurons. So if we do this one on every single neuron in our network, we call this one as a feed forward or forward propagation, moving from the input layer to output layer and doing this calculation for each single neurons in our network. So at this stage, we need to talk about cost function, loss function, or error function. Actually, all of these three terms refer to the same things, actually, because at this stage, we need to do some optimization. So when we are talking about optimization, actually, we want to do minimization or we want to do maximization. If we want to do maximization, we call the objective function as, for example, profit function or utility function. If we want to do minimization, we call it cost function or, for example, error function or loss function. Because in our daily life, we all are trying to minimize our costs and we are trying to maximize our profit. So the terms here is similar to the optimization because by the end we want to reduce the error in our system. This is for this purpose, we need to use a function, which that function is called cost function or loss function. So let's look at let me move to okay. When we are doing the first iteration or the first feed forward step, we thought that we need to calculate. We need to do that operation for this single neurons. These operations actually, but we haven't talked about how we need to choose the right value for the weights and biases. So, for example, in this network, actually there are 784 input, and we had 15 hidden layer neurons in the hidden layer, and also 10 neurons in output layer. So let's do a simple calculation to know how many weights and biases we have in this network. So for example, the number of weights is 784 times 15 plus the number of the weights here and the number of weights here times 10. Which is maybe somewhere more than 50,000 weight we have in this example, or 5,000. Let me do a simple calculation. Okay, 784 times 15. Oh, okay, that's 11,000. All right, so. That's about 760 weights we have here, and we have 150 here. So you see that we have lots of number of weights here. So actually what we need to do is to assign weights and biases, all weights and biases here randomly, because of course we cannot assign more than 11,000 weights manually. So we pick this one randomly. We pick some random numbers for this weight and some random number for this bias here. So in the first iteration or first feed forward step, we assign all the weights and biases in our networks randomly. So we assume that how the output of our model will be looked like. If we assign a massive number of random numbers, so the output won't make sense, or it cannot do a accurate prediction. So, for example, assume that we feed our networks with a number. Yeah, we feed this network with a number 4, and what we expect that we have a, for example, very positive number here, like 0.8. And if our networks work well, we expect that the output of this, the rest of the digits will be some small numbers, for example, and only we have a big number here for digit 4, that we can choose this one as the output of our classification in this problem. But so this is if our network will work well, we expect some output like this. But in an ideal case, we expect that the output for the other digits be 0, and only for this one be 1. So in this case, we can see that there is a difference between our calculation, that the output of our network and our ideal or expected value. So we can calculate this one as an error. So if you assume that we fit all of our we assign all of our weights and biases randomly, so the output maybe make some irrelevant numbers in output. For example, maybe 0.7, 0.5, 0.6, 0, and for this one that we are interested, maybe assign a small number. So this is, for example, the output of first feed forward. So we can see that there is a difference between these two. So in this case, what we need to calculate the error between the output from the first iteration and the expected. So we can calculate it simply as 0.7 minus our desired value to the power of 2, and repeating this one for doing this calculation for all of the 10 outputs. Then finally we come out with a number which is our error. But this error we need to take into account that we are calculating this error for only one single neuron. What we need to do is we need to repeat. Sorry, this error is related to one sample. What we need to do is calculating this error for all samples and taking average. And by the end of the first feed forward, we can calculate the error, and based on this error, we can say how good or how bad our weights and biases is. So after this, we need to take a backward movement. So far, we move forward. That's what we call it, forward propagation. We need to take a back movement. We call it back propagation. The purpose of propagation is to updating the weights, all weights and biases in our network to improve the performance of our system for minimizing that error, which is equivalent to minimizing the cost function. For this purpose, we need to do some calculus to calculate the derivative. So the purpose is that we can understand based on this that how much, for example, changes in weight or bias make a change in our output layer of the next neuron. So for this purpose, I'm not sure whether you're familiar with the definition of a gradient or not. The gradient actually indicates the direction that we need to take to increase the value of our function. So if we consider the negative of gradient, it shows us that in which direction we should move to reduce our cost function. You assume that this is the cost function for the one neuron. Actually, in the reality, it's not similar. This because the dimension of the problem is equivalent to the total number of bits in one network, which in our previous example, that was similar to 11,000 something. That's the dimensionality of the problem. But for the sake of simplicity, I use this figure, a 3D figure that makes sense that how gradient descent works. So gradient descent is actually the negative of gradient that we apply on the loss function on whole of the weights. And based on this, we can calculate, we can come out with a vector like this one, that each element in this vector is correspond to a number that can be, for example, a positive number, it can be a negative number, it can be a large number, a small number. These numbers show that how that particular weights need to be revised. So based on that, we revise our weights, and we repeat that steps again. So far, we started to move from the input layer to the output layer. Then we call that forward propagation. This is backward propagation. And if we do this iteration for one single sample, we call it one iteration. And if we do the same procedure for all samples, we call it one epoch. So I try to summarize the neural network in a few minutes. The topic is not straightforward, actually. I did my best to summarize the neural network, but if you are still confused, don't worry. I provided two links here. One is for one free online book with, that teach the same problem, handwritten digit recognition with codes, and walk you step by step. If you are interested in the topic, you can read this book. Or if you want to understand deep learning in less than 1 minute, I strongly recommend you that after this today, you spend less than 1 hour to watch this full video on YouTube. That's some short video with great animations that that show you how neural networks work in for this problem. So I hope by the end of this introduction, you are now clear about some definitions like neuron and nodes, about activation, about the weight, about the bias, about the activation function, input, output, hidden layers, feed forward, back forward, cost function, loss function, iteration, and impulse. Because being, for example, when you are working with edge impulse, you may need to change if the number for equals, or changing the iterations, or for example, changing the learning rate. Okay, the learning rate is the size of the step that we actually take to reach to the global minimum. So if this step is big, we can assign, if you want to this step be big, we can assign a large number to learning rate. But it's advised that for first iteration, it can be, for example, a large number of, but for the rest of that, we can assign a very small step size that can reach to the global minimum. So that's all about the neural network. So let's just quickly review some of the tools that we need to use to create a machine learning project. Actually, you can create your machine learning project in the three different ways, actually. The first one, generally, that's a general categories. It's not actually a precise one. So for this case, you may want to use the IDE or some, for example, editors like VS Code, Spider, or PyTorch that you do your coding in these editors, or you can use some web-based or cloud-based platform or notebooks for doing the coding, or you can use Edge Impulse, which is a great tool that helps you to do your coding and do your TinyML project. So one thing that we need to take into account is if you that is up to you to choose which one in your project. So if you want to do some installation, you want to do some, for example, advanced coding, you can go for the left one. If you don't want to do some installation and doing some general coding, like what we did yesterday, you can use, for example, Jupyter or Colab. So that's up to you. So let's define that what Colab actually is. It's a executable document that allow you to write and run your code on a cloud and share your code with others. Actually, it's like a version of Jupyter Notebook that can be stored in Google Drive. So later you can share your code with Google Drive or GitHub. So also allow you to do some collaboration work on your code. Also it provides some hardware acceleration like GPUs and TPUs that you can run your heavy data set in a shorter time rather than waiting, for example, for weeks or months to run those codes on your personal computer. So if you want to use the Colab, the things that you need to do is just simply search for Colab research google.com. So then you can create a new notebook for yourself, and you can start writing your code here. For example, simply you can start coding without the need of any installation. So, for example, just by pressing the Enter and Shift, you can run your codes on the cloud, and also you can share your codes with others. Also, you can, for example, save on a GitHub, and also you here in a runtime, you can change, for example, your runtime to GPU or TPU. So, one of the most important libraries that is so popular in using that data scientists are using actually is Pandas. So it's actually the number, the volume of data is rapidly increasing. Now, what we need powerful tools that are flexible and also advanced for analyzing those large amount of data. You assume that, for example, you are planning to analyze a data set in a size of 1 million, and you are collecting those data from, for example, 50 different sources. So actually, it might be difficult for you or impossible that you use some conventional tools like Excel or Google Sheet for those data analysis. So that's why that we are using Pandas. For this purpose, actually, we can read data, for example, from CSV files, and we can work on series, do some arithmetic, statistical operations. We can sort our data and also work with data frames, and also choosing row, columns, filtering, and it also optimize our memory. So these Pandas is too helpful, especially during our data preparation and also pre-processing and data cleaning. Is why we can be used. So for this is from my point of view, an individual topic that you can spend your time to learn Pandas. So if you want to learn this one as a first step, you can go to the Pandas website. From getting start, you can access to some tutorials and materials to start learning Pandas. So you can refer to the Pandas pydata.org to start your learning Pandas. NumPy is actually something similar to MATLAB that does some operation on array and matrices. So it's another famous library among the data scientists. So actually, we can use this one to create array for indexing, slicing, and doing lots of logical sorting, selecting, and for lots of purposes, we can use this one. There are lots of, for example, if you remember yesterday, we talked about feature extraction. So this is where, for example, we can use NumPy for feature extraction, and also we can use this one, for example, for data cleaning as well. So for this one also, if you are not familiar, you can go to numpy.org.
Oh, we lost you, Mehran. Hello, Mehran. Are you still there?
Also,
Oh,
hello.
Mehran, we lost you for the last minute or so.
Oh, okay. Sorry. Yeah, suddenly I think my Zoom has been closed. Sorry. So I think I need to share my screen again. So
Okay. Yeah.
okay. So scikit-learn is a scikit-learn is one open source machine learning library that is a general library that covers most of the models in general models in machine learning, and is also widely used with the machine learning developers. On the other hand, we have TensorFlow, which is open source end-to-end platform. The difference between TensorFlow and scikit-learn can be, we can say that TensorFlow has a wide application in deep learning and neural network, while scikit-learn is generally can be used for machine learning. But TensorFlow is more popular for deep learning and also for neural network. So it provides a wide range of APIs also for different programming languages like Python, C++, and also is developed and supported by Google. So the question at this stage is it possible that we use TensorFlow in our TinyML devices? So that's why the Google developed TensorFlow Lite for this purpose, that it does some optimization on the TensorFlow algorithms to make it possible to model tiny machine learning on tiny devices. So let's dive to this slide. So if you want to use a Colab, so there is no installation, so you can just Google it and open it and use it, and you can easily do your coding here. But if you want to use these libraries on your IDE, so you need to install these libraries separately. So if you are a Linux or a macOS user, so Python already has been installed in your system. What you need to do, you need to install this library. But if you are a Windows user, so in this case, what you need to do is actually install these stuff separately also. So to make it easier, you can use you can install Anaconda. So when you install Anaconda, the most important libraries will be installed on your system at once. So it will help you to prevent installing things separately. So last but not least, which is the topic of the next session, is using Edge Impulse for your TinyML projects. Is a great tool to create machine learning projects, which makes the modeling much more easier because it provides graphical interface that you can easily model your model. You can train your model, and rather than focusing on programming stuff, you can focus on your problem to solve it. And it has a great visualization interface that you can see that what is happening in your data and in your model, which is great, but that's the topic of the next session. So I think we have another 10 minutes. So let's do some coding and Colab. So see how the example of neural networks work in a programming environment. So for this purpose, like yesterday, and like all other Python programming, we need to import the required libraries. So first we import required libraries. So we are using, at this stage, we are using MS dataset. MS dataset provides a large dataset for from the handwritten digits. So let me share with you the CSV file of the MS. Yeah. It's a large data set, if I'm not mistaken, about 70,000 samples from different digits that collected. It's an extensive data set. So we are going to use this data set and machine learning to solve the problem of the handwritten digit recognition. And so I'm waiting for the Colab to read this file because this file is too heavy. So it takes time. So yeah, it's finished. So let me also share with you. Yeah, I'm still waiting to open the CSV. Okay, as you can see, there are actually about 70,000 samples from handwritten digit. So as you can see, each row belongs to one sample, and each column is a corresponding pixel of that sample. So 0 is for the black color. So if we move to the right side, we can see the changes here, that these changes actually belongs to the gray or maybe white color. So by the end, the last column is our class. For example, the data in the first row is for 5, and the second row is for 0, 4, 1, and so on. So you can see that the dimension of this data set is too big, 7,000 by 780. How much was that? 784 pixels. So first we read the data and we normalize it by dividing by each elements by 255. So if you want to see the shape of our data set is a 70,000 sample, and each sample contains 784 features. And this is the output. If we want to look into in our outputs, and we can here divide, our data already has been cleaned, so we don't need to do some pre-processing on our data. So we only divide our samples into, for example, we pick the first 60,000 samples as a train, and we pick the last 10,000 as a training set. So here, what we need to do, we are using the multilinear perceptron classifier, and we set it to 50, which is the number of nodes per layer, and also the maximum of iteration. If you know, if you remember from my slides, number of iteration, this is the, for example, learning rate. So we are using the, for example, gradient descent as solver. So for these cases, I will suggest you, if you are not familiar that how a function works, the things that you need to do is just simply Google it. So for example, if you Google it, in SciTinyML, there is a description that, for example, what each of these parameters actually is. For example, it's also said that a default number is 100. And the activation, we can choose from logistic, temp-edge, remove. So we have for solver, we can use Adler, we can use, for example, gradient descent. Yeah, this is our option in choosing the right solver or parameter in our model. So then we can train our model. We can set the parameter for our model, and then we can start training our model. It may take maybe a few seconds. Yes. So here what you can see here is that our loss function is too much in the first iteration, because in the first iteration we pick the weights and bias randomly. That's why we can see a large loss in first iteration. And we can see that how dramatically it starts to reduce the iterations. So here in our model, we define the maximum number of iterations is 100. So when we say the maximum number of iterations, the algorithm may stop doing calculation before 100. So in the purpose of this phenomenon is, for example, if until this algorithm is running, let me to show you that what does it mean. When you assume that, for example, here, for example, if this is the error and this is the number of iterations, it's dramatically start to decrease, and after that we don't see any improvement in our error function. So in this case, to save the, for example, our computation power or resources, we may tell the algorithm or algorithm it does this one automatically. If after, for example, a fixed number of iteration, it doesn't see any improvement, it stop the training procedure. It also can prevent overfitting in our problem, in our training procedure. So as you can see, it's in the it's running, and my time is about to be finished. So I will share this code with you. You can run this code by yourself. The data set is free and can be accessed from the scikit-learn, so you don't need to download by yourself. And after this iteration, after a few iterations, stop training the model and will stop the training procedure. As you can see that the loss has been decreased to very little. So, yep. And later we can measure the performance of our system. So I think
should we see if there's any question for the next?
If
for the next 2 minutes.
Question, please ask your question.
First of all, thank you very much again, and clapping hands for your great presentation. And it's a challenge to present, a complete kind of ML course in few hours, but you did it really successfully. So, are there any questions for Mehran?
If there is question, you also can ask me on Discord. I try my best to answer, and I hope I could give you enough enthusiasm and a good basic knowledge about machine learning. I hope that these materials encourage you.
Mehran, there's 2 questions. Oh, there's 3 questions in the chat. So the first one is, can you run this example, this data set, the MNIST data set in Edge Impulse? And I think that's a question for you and for Luis that is going to lecture next.
I think Edge Impulse is capable to do this model, but I'm not sure.
Okay.
You can implement it in TinyML or not. Maybe you need to use minimize this.
Okay, so we'll keep this question for Luis for the next section. And then they're asking, if you're doing ML training in Colab, how can you improve the training speed?
Okay, you can come in your runtime, and from here you can change the runtime type. For example, this is a normal noun. You can change it to GPU or TPU. By changing this from GPU to TPU, you can take advantage from cloud and run your code much more faster.
Okay. And there's even a paid solution, I believe, right?
Yeah.
This Colab Plus, maybe you get some more GPU and TPU time. Yeah. Okay. And then asking, what is the difference between iteration and epoch?
Okay, iteration is actually feed forward and backward on one sample. Epoch is iteration for forward and backward on all sample. For example, if we have 100 sample, if we do the forward and backward for all of them, we call that epoch. And if we do this procedure for one sample, that is iteration.
Excellent. And then final question, is the sigmoid activation always perform well for multi-classification?
For this problem, that is simple, so it may work well. But for complex one, yeah, it has been proved that Redu works better because of this low computational complexity.
Excellent. So again, thank you very much, Mehran.